The discovery of dark energy represents one of the most profound revolutions in modern cosmology, fundamentally altering our understanding of the universe's composition and destiny. This mysterious force, constituting approximately 68–70% of the universe's total energy density, drives the accelerating expansion of space, a phenomenon first observed through Type Ia supernova measurements in 1998. While ordinary and dark matter collectively account for just 31% of the cosmic budget, dark energy's dominance has reshaped gravitational dynamics on cosmological scales, counteracting matter's attractive pull with a repulsive effect that grows stronger as the universe expands. The implications extend from the large-scale structure of the cosmos to the ultimate fate of all celestial structures, making dark energy a cornerstone of contemporary astrophysical research. The paradigm shift began with meticulous observations of Type Ia supernovae, stellar explosions whose consistent intrinsic brightness makes them ideal standard candles for measuring cosmic distances. Two independent teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, found that distant supernova appeared dimmer than expected in a decelerating universe dominated by matter. This unexpected dimming implied that galaxies were receding faster than predicted, with the expansion rate accelerating over the past 5 billion years, rather than slowing under gravity's influence. The 2011 Nobel Prize in Physics recognized this breakthrough, awarded to Perlmutter, Schmidt, and Rees for their leadership in unveiling cosmic acceleration. Subsequent verification came through multiple cosmological probes. Cosmic microwave background, CMB measurements from the Planck spacecraft revealed a geometrically flat universe requiring dark energy's presence to balance the energy density. Baryon acoustic oscillations, frozen density waves from the early universe, provided independent confirmation by serving as standard rulers to track expansion history. Gravitational lensing surveys further constrained dark energy's properties by mapping the distribution of mass and its growth over cosmic time. These converging lines of evidence established dark energy not as an observational anomaly, but as a fundamental component of the cosmos. The leading theoretical interpretation posits dark energy as Einstein's cosmological constant, a static energy density inherent to the vacuum of space itself. Introduced then discarded by Einstein in 1917 to maintain a static universe, it found redemption through these observations, providing a mathematically simple solution where vacuum energy exerts negative pressure, driving exponential expansion. In the L-CDM, cold dark matter model, this constant accounts for 70% of the universe's energy budget, with dark matter, 24%, and baryonic matter, 5%, comprising the remainder. Alternative theories propose dynamic scalar fields like quintessence, where dark energy's density evolves over time. Unlike the cosmological constant, quintessence fields could interact with dark matter or vary in strength, potentially resolving the coincidence problem, why dark energy became dominant so recently in cosmic history. More exotic hypotheses include phantom energy models predicting a Big Rip scenario where expansion tears apart galaxies, stars, and even space-time itself. However, current observational data from projects like the Dark Energy Survey, DES, and Baryon Oscillation Spectroscopic Survey, BOSS, align most closely with the L-CDM predictions, favoring a cosmological constant. Dark energy's repulsive effect stems from its unique equation of state, quantified by the ratio of pressure to density, W. For the cosmological constant, W equals 1, implying negative pressure that remains constant as the universe expands. As space stretches, matter density dilutes proportionally to volume, while dark energy's density remains nearly invariant. Approximately 9 billion years after the Big Bang, the scales tipped. Dark energy surpassed matter's density, initiating the current epoch of accelerated expansion. This transition marked a cosmic inflection point. During the universe's first half, matter's gravitational pull decelerated expansion, allowing structures like galaxies and clusters to form. Once dark energy dominated, its repulsive gravity began pushing galaxies apart at ever-increasing rates. Critically, this acceleration operates not through a force in the classical sense, but through geometry, Dark energy modifies the Friedmann equations governing cosmic expansion, altering the Hubble parameters evolution. The universe's accelerated expansion leaves distinct imprints on observable phenomena. Photons from distant supernovae experience greater redshift than expected in a matter-dominated cosmos, a telltale signature of dark energy. Large-scale structure surveys detect suppressed growth of cosmic voids and filaments, as accelerated expansion limits gravitational collapse. Even the CMB's angular power spectrum reflects dark energy's influence, with temperature fluctuations constraining the universe's flatness and energy composition. Looking ahead, dark energy's dominance portends a profoundly isolated cosmic future. Current models project that within 150 billion years, all galaxies beyond the local group will redshift beyond detectability as they cross the cosmological event horizon, a boundary where recession velocities exceed light speed due to metric expansion. While the local group remains gravitationally bound, the rest of the observable universe will fade from view, culminating in a heat death scenario where entropy maximizes and structure formation ceases. Phantom energy models predict more violent ends, with the Big Rip dissolving all bound structures billions of years before heat death. Major observational initiatives continue to refine our understanding of dark energy's nature. The Legacy Survey of Space and Time, LSST, at the Vera Rubin Observatory will catalog 20 billion galaxies, measuring cosmic shear and baryon acoustic oscillations to unprecedented precision. NASA's Nancy Grace Roman Space Telescope will complement these efforts with high-resolution infrared surveys, probing the universe's expansion history across 10 billion light-years. Ground-based experiments like DESI, Dark Energy Spectroscopic Instrument, are mapping 35 million galaxies to reconstruct the large-scale structure's 3D distribution. Key unanswered questions persist. If dark energy is the cosmological constant, why does its observed energy density differ so drastically from quantum field theory predictions? A discrepancy of 120 orders of magnitude? Dynamic models like quintessence attempt to resolve this cosmological constant problem, but lack empirical support. Dark energy stands as both a triumph and a challenge for modern cosmology. Its discovery validated general relativity's capacity to describe the universe at grand scales, while exposing critical gaps in our understanding of quantum vacuum energy. As observational campaigns gather petabytes of data, the coming decade may determine whether dark energy truly represents Einstein's resurrected constant or a dynamic new field awaiting discovery. Regardless of its ultimate nature, dark energy has irrevocably altered our cosmic narrative, revealing a universe dominated not by visible matter, but by enigmatic forces shaping space-time itself. The quest to unravel this mystery continues to drive innovation in theoretical physics and astronomical instrumentation, ensuring dark energy remains central to humanity's exploration of the cosmos.